Yay!
Yay! All right, next object. How about now we try a solid sphere? This one you might see less commonly done in textbooks. Usually just write down the answer, but let's go ahead and figure it out because it's kind of fun to do. Again, let's build on what we did before. So we first figured out the moment of inertia of a ring or a hoop, and then we integrated a whole bunch of those to get a disk, to sweep out a disk. Let's use what we've already done. We know the I for a disk is 1/2 mr squared, right? I know that already. So one way that I can sweep out a solid sphere is to integrate a whole bunch of disks. Since we've already got the result, let's just use it. So what I'm going to imagine is starting out with a disk right here in the middle of this thing, and then sweeping out a whole bunch of disks until I reach the edge of the sphere. Now they're all going to be changing size, right? They've all got a different... let me clean this up. They've all got a different R. They've all got a different size R. But those are just going to be disks, and I'm just going to add a whole bunch of them together. And if I do that, I should get a sphere. So that's what I'm going to do. Now, each one is going to be really, really thin. So each one has a mass dm. Okay, so once again, we start with this. I is the integral of dm. Oops. It's 1/2 mr squared, right? So it's going to be, each one is going to be 1/2. It'll have a mass of dm, and it's going to have a radius of little r squared. Okay. And then I'm going to be integrating from 0 out to big R, right? From the middle out to the edge of the sphere, out to the radius of the sphere. So I'm going to be integrating 0 to R. What am I integrating? What is the thing? This is often what you have to sit down and think carefully about. What am I integrating? What's the variable? I'm integrating along x, right? That's the axis about which this thing is going to spin. I'm integrating these things along x. So I'm going to have to get this thing eventually in terms of x. So that's going to take a little bit of work because there's no x's in there right now. Okay, one step at a time. First of all, let's get the dm's in terms of r's. Let's change our variables, and then we can worry about the x. Okay, so we use the same trick that we did before. In terms of, so each little disk is a mass, right? A mass dm. Except now I'm sweeping out a volume and not an area. So here we go again. A little bit of mass compared with the whole mass. If this is a uniform sphere, then this is going to be like a little bit of volume I'll do it in words first, compared with the whole volume. Right? All right, little volume. Well, the whole volume is going to be easy. What's the volume of the sphere? 4/3 pi big R cubed. Okay, no problem. What's the little volume? What's the volume of one of those little disks? Well, it's just going to be the area times the thickness. All right. What's the area of a little disk? It's just going to be pi times r squared times, what is the thickness of those disks? Well, I'm integrating along that direction x, right? And so the thickness of each of those things is just going to be dx. Aha, there's where my integration variable is going to come from. So there's the thickness. Now I can cancel pi out of there, right? So dm over m is what the 3 pops up top. So it's just going to be 3r squared dx over 4 big R cubed. All right. So now I can plug that into here. Let's see what we get. So the moment of inertia is then, it's going to be 0 to r. Okay, I got my 3 over 4. Okay, but I've already got a half in there to begin with, right? So this is going to become 3. I'm going to have a big M. What else? I'm going to have an r squared dx over, on the bottom, I'm going to have an 8, because I had a 2 there already, r cubed. And then I already had another r squared. It was there originally, and now, oh, I got my dx. I already figured that in. Okay, so let me just do this. Becomes an r to the 4th. All right. So now I have to relate the r. What is the relationship between the radius of each of those disks and x, the distance along which we're going? Well, look, that's a little right triangle, right? It should be true that big R squared is just x squared plus little r squared. So look what I can do. I can say that little r squared is just r squared, big R squared minus x squared. Aha! So r to the 4th, I'm just going to square that thing, and now I have it in terms of x. There's my integration variable. So look, here's what I'm saying. This is just going to be, let me bring some of those constants out front. 3m over 8r cubed. I'm going to have a 0 to r, right? And then I've got r to the 4th. So this is going to be r squared minus x squared squared. There we go. Times cx. How about that? It's not an obviously elementary integral, but it can be. I mean, if you leave it in that form, you know, like if I let u equal r squared minus x squared, you're going to get in trouble because we don't have the extra x. But I say, let's just multiply it out. If we multiply it out, it's just a polynomial, and that'll be pretty easy to integrate. So this is going to be equal to 3m over 8r cubed. 0 to r. I mean, just multiply this thing out. I'm going to have an r to the 4th minus 2r squared x squared plus x to the 4th dx. Okay, now that's not going to be a problem. That's going to be pretty easy. So this is 3m over 8r cubed. And in all of these, when I plug in my limits, I don't get anything for the bottom limit, 0, right? And for the top limit, I'm just going to get big R. So, okay, take the first one, r to the 4th dx. Well, that's just going to be r to the 4th times x. Plug in the r, and I just get r to the 5th. Let's see. Now I get minus 2r squared x squared. So that's going to be x cubed over 3. So it's going to be minus 2/3. And that x cubed, I've already got an r squared, that's going to be r to the 5th. These should all turn out to be r to the 5th, right? Because they're all being added or subtracted together. So they should have the same exponent. Okay, x to the 4th, that's going to be x to the 5th over 5. Substitute big R, r to the 5th over 5. I mean, there we go. I better simplify that thing on the inside. What's the common denominator? Like 15, right? So I got 15 minus 15 r to the 5ths minus 10 15ths r to the 5ths plus 3. So 15 minus 10 plus 3 is 8. So this is going to be equal to 3m over 8r cubed. And after all this, I should wind up with like 8 15ths. R to the 5th. I'm almost home. Look. The 8 goes away. And 3/15ths, what is that? That's 1/5. Oh, but remember, we only did half the sphere. This is going from the center out to the right, right? Well, all we have to do is double it to get the whole sphere. I've only done half the sphere. So if I want the whole sphere, I just double it. So that means that for the solid sphere, I had 1/5. If I double it, I'm going to get 2/5. So this is just going to be 2/5 mr squared. To make a better box. All right, there we go. So that's how to figure out, that's how to actually calculate with calculus the moment of inertia of a solid sphere. Cool. The only one left that we're going to want to do is a hollow sphere, and that's a little trickier.